All right, so let's look at some analyzing piecewise functions. So first thing we're going to do is we're going to given the fact that we have this piecewise function given to us, we're going to graph it first. Okay, so we have negative 2x plus 1, and we're going to graph that line, that linear portion of our piecewise, and it's going to go between negative 2 inclusive all the way to 1. All right, so we're having our line, it's going from negative 2, all right, to 1. In that portion, we can definitely see our y-intercept right here of 1 falls in that interval of x's. And then, of course, we can then incorporate our slopes. So up 2, left 1, up 2, left 1. Or we can go down 2, right 1. Okay, and this would be our line that would be created. Now, if I were to go all the way across and create our line, erase the stuff that's on the x-axis I did there, it would look like this. Now, one thing we notice about our interval is it's negative 2 to 1. Remember, negative 2 is included, 1 is not. So we need to go back over here. Negative 2 has a solid point, that x value right there. So we're going to leave that as a solid, whereas our x value of 1, y value negative 1, this point is going to be an open circle because it's not included. Okay, then the second portion of our piecewise function is that y is equal to 2 when x is 1. So we go x is 1, y is equal to 2. That would literally just be a point. Okay, and the last portion of our graph is to graph y equals x squared. We're only going to graph it from the interval 1 to infinity. So typically x squared, right, would be right here at 0, 0, and then at 1, 1. And then at 2, 4, and then we could graph our parabola, same thing over here, negative 1, 1, negative 2, 4, but we're only going to be going from 1 to infinity. So we go back. These values are not included. All right, we only care about, here's our first point that matters. We'll go ahead and make it into a blue point now. And then there's a second one, obviously it continues to go on forever. Last thing we want to double check is the fact that this is an open interval on the 1. So this point right here that we first indicated needs to be an open circle. And now we have our parabola going a little bit better. Our parabola that's now increasing forever to infinity. Okay, part B. Find f of negative 1, f of 1 and 2. We can use it either use the graph or we can just go back and use our equation and plug it in for the appropriate portion, the appropriate piece. So f of negative 1 would fall in this interval. So we're going to use the negative 2x plus 1. So negative 2 times negative 1 plus 1 would be 3. F of 1, well, that's when x is equal to 1, which we know is that point we talked about earlier. It's literally just 2. And then f of 2 would fall in now our final interval here. So that would be the quadratic portion. So 2 squared, and we plug that in with n equal 4. All right, the domain. The domain for our function. I know it is in pieces over here. We can notice that it's actually pretty nice. You can see, hey, negative 2, all the way to negative 1, all the way to 0. Let's kind of make sure you can see what I'm actually talking about here. Negative 2, all the way to negative 1, all the way to 0. And we're going to continue to get all the way down here until when x is 1. There's an open circle, but we jump up to this spot, and there it is. It's accounted for right here. And then we start going, again, 1 all the way into infinity. So all of those values are actually included. So we can say there are no gaps. It would be negative 2 inclusive all the way to infinity. Of course, we have an open parentheses there on infinity. Okay, and the range, you can look at it the same way. It looks like all the values from the lowest it goes is negative 1, but it's not included. So I put negative 1, comma, and it goes all the way up to all of these values along our linear path until it stops, right, at negative 2, what would that be, 5? But over here on the right, all these values are included again, all the way up to infinity, because we have our arrow here, obviously. So every value is accounted for from negative 1 up, not including negative 1. Okay, now intercepts. our x-intercept, and then our y-intercept. Okay, I'm going to go ahead and do the y-intercept first. It's just plain as day. You can see it's 0, 1. Okay, we got that from our original linear function. X-intercept might be a little more difficult, but we can see the x-intercept occurs. Do this in red. Occurs right. Let me pick a different one. How about in black? That's fine. Right here. There's our x-intercept. That's on the linear portion of our piecewise. So I'm going to go over here and use this negative 2x plus 1. We'll go up to the side. Negative 2x plus 1, we're looking for when that crosses the x-axis. That would be when y is equal to 0. And so we can solve this particular equation, subtract 1, and then divide by 2. We get x is 1/2. So we know that x is 1/2 when y is 0, which represents our x-intercept. Okay, the last question given to us is f of x continuous on its domain. I'm going to go into this more in detail with limits, but for right now, can you create that graph without having to pick your pencil up? And you can see if we're drawing a graph, with an outline over here. If we're creating our graph, we also at this point right here. And then we started coming down. We're all good. We had to pick our pencil up to create this hole. Create our pencil up to go over here and make this point. Pick our pencil up. Continue going on. This is, without question, not continuous. All right, that's not continuous. And I'll go over continuity with limits later on. I need to be careful with this right here as far as picking our pencil up at this hole, but like I said, I'll go more in detail later on. You have to pick your pencil up to create 3 portions of that graph because they're all separated. All right, so that's another example 2. Write these following functions as piecewise. So absolute value of x looks like this. That'd be a parent function you need to know by heart. Okay, where the slope on this left side is -1, and the slope on this right side is +1. It's actually just a line going through the origin. So we can just rewrite that function as a piecewise. Make it a little bigger. There we go. Okay, it is -x there on the left, and it's +x, just a line, on the right, both of them, one with the slope of -1, it's our original -x, and then the slope of +1 with our x. The -x occurs from -infinity all the way to 0, and then the x occurs from 0 all the way to infinity. And then since this 0 is defined at this spot, we need to have a bracket on one of these so that it's included. And the function is continuous, so it doesn't matter which one in this case. So there's our piecewise for an absolute value. All right, I'm going to erase that. And now it just has some space for this last one. So g of x equals this absolute value of x minus 1 over x minus 1. This is one that AP has really enjoyed going to. If you go and plug values in and check this out, you're going to notice some things that are interesting. First one is that x can never equal 1 because that would produce a 0 in the denominator. But if you plug in values of 1, 1.1, 1.2, 2, 3, 4, 5, and continue going from 1, everything to the right, you're going to notice again, we can't be 1, so I have an open circle, but everything else, when you divide, is going to equal 1. So it's going to be a graph from x equals 1 to the right, all the y values are equal to 1. Okay, and then if we plug values in that are less than the x value of 1, we actually get -1. Of course, we can't have, when x is 1, we cannot have a value, because it's, again, divided by 0, but if you start plugging all these other x values in, you get a y value that's -1. So that's what our graph actually looks like. So we have g of x over here. We're going to create a piecewise for it. Okay, we have it's either equal to 1 or -1. So I write -1 and 1. It's equal to -1 from -infinity all the way to 1, not included because it's an open circle. And then it's equal to 1 from 1 all the way to infinity. All right, here's one application I'll do with you. It's an energy, like an electricity providing example. So we have this company that's going to charge $5.50, a monthly customer charge of $5.50, plus 6.4471 cents per kilowatt hour for the first 1,000, kilowatt hours supplied in the month, and then they're going to hike up the price to even higher, to 7.8391 cents per kilowatt hours for anything that's over 1,000. All right, so the first thing is, what's the charge for using 300 kilowatt hours in a month? All right, so our charge, okay, I'll just write it as an expression here. It would be $5.50, no matter what. You have to pay that monthly customer charge of $5.50. And then tack on our energy usage, which in this case is 300 kilowatt hours. Now, since $5.50 is in dollars, it's $5.50, we need to convert this 6.4471 to where it matches with the $5.50. So we'd actually move the decimal place over 2 times to the left to make it more like, hey, 6 cents in the dollar sense, so 0.064471. Okay, that's how much it costs per kilowatt hour, and we have 300 of those in our first part here. All right, so for part B, it's the same thing, but this time, what's the charge for using 1,500? So we're still going to have our monthly service charge no matter what. We're going to have to pay some money for that first 1,000, right? Because this 1,500 is over the 1,000 kilowatt hours. So we have something a little bit different here. So we're going to first pay the 0.064471 times 1,000, because that's the price for the first 1,000 kilowatt hours. And then after that, they hike up the price to make it a little bit more expensive to that 0.078391. And we've already paid for the first 1,000. We only do this for the stuff that's over 1,000. So 1,500, that means just 500 more kilowatt hours we have to pay for. And that's going to be at that higher price that we mentioned before. Okay, so part C is saying what is development model, like a piecewise function here to represent our situation. C is the monthly charge for X kilowatt hours, so we say C of X equals, all right? And instead of using these specific numbers like we did earlier, they're going to be any for a monthly charge X. So we could actually kind of go back up here, and these spots that we had actual values in, oh, let me change that color, sorry. There we go. So right here, and right here, we're going to need to represent those as some type of variable, or an adjustment. And so our first thing is, if it's 0 to 1,000, we know we're going to, that's like example A here, it's $5.50 plus the 0.064471. And for any value X, I'll just say X. That's for how many kilowatt hours. That's if we have anywhere from 0 to 1,000 kilowatt hours. And I put brackets on both. I can put a bracket in the 0 because no matter what, we have to pay that $5.50 monthly customer charge. And then we're going to have all up to 1,000 is this price. Now, if it goes over 1,000, we still have to pay. I'm kind of looking at part B now. We still have to pay the $5.50. We still have to pay for that first 1,000 kilowatt hours. So 0.064471 times 1,000. Okay, because that's going to max out that portion. So now we're looking at this last part over here that we did, the plus 0.078391, the higher price, but that's only for the stuff that's over 1,000. So we're going to say, hey, if you look back at the beginning, that would have been, to get the 500, we said 1,500 minus the 1,000. So we've already paid for that first 1,000, we just need whatever's left over. So whatever we use, X minus 1,000 is the part that we're going to multiply by with that higher price. Okay, and the only thing we need to indicate now is the interval, and I can't really fit it, I put it down here below. That's for anything that's 1,000 or higher. Okay, so that'd be like our interval for that second part of our piecewise function. All right, so the last part of these notes is if I gave you a piecewise function graph and asked you to create an equation from it, and I'll go ahead and tell you this. This portion right here is the first part of our graph that we are going to try to find a function for. And then we have this middle portion in orange, And then lastly, we have this part right over here. So that's three parts of our piecewise function. We have a cubic, a linear graph, and a quadratic portion of our graph. Okay, so if this function was, let's just say it's f of x, then we say f of x equals, okay, so look at the part in green. Okay, the part in green, like I said, is cubic. It's no stretch or anything like that, compression. So basically a cubic would typically start at the origin, but ours is actually passing through the point -3, 0, which means we would shift our cubic to the left 3. So that's when you put parentheses and you change the value on the x. So x plus 3, right, would move something to the left, and that would be cubic, so put a little 3. And that occurs, and put arrows on this graph, let's go forever. So from -infinity all the way to -3 is our cubic portion of our graph. Okay, so now we're looking at the part in orange. All right, so that's our line. We can look at our slope. We can see that our slope is up 1/3, so we know it's going to be a slope of 1/3 x. All right, and then you can use a lot of strategies to figure out what the y-intercept would be. You can use just really, to be honest, you can use a little bit of reasoning and figure this out without doing any algebra, but if you don't see it, that's totally fine. All you need is two things to create the equation of a line. You need a point and a slope. Well, we have a point right here, and we have a point right here. We just pick one of them. Okay, I'll pick the one on the left, -2, 1. So here's our point, -2, 1. And then we already know our slope, we got that earlier, is 1/3. So we can go to our point slope form. So y minus 1 equals 1/3 times x minus -2, so x plus 2. We can distribute our 1/3, so that's 1/3 x plus 2/3. Add our 1 over, and we get 2/3 plus 3/3, which is 5/3. So that y-intercept is actually 5/3. So we say 1/3 x plus 5/3 would be the equation of the orange line, and that happens between, ooh, I messed up on it earlier, I apologize. Let me go fix that real quick. Our cubic did not go to -3. There we go, went to -2, right? So to -infinity to -2. Okay, that's fixed. Now we have our linear portion, which is -2. Again, you can put a bracket, parentheses, but I've already incorporated the bracket from above. It's a continuous function, so I don't have to worry about anything different. So I'll just put parentheses this time. -2 all the way until we get to, what is this? Be careful this time. 1. So -2 to 1 would be the linear portion of our graph. Again, I put parentheses. You could put a bracket. As long as we incorporate one of them, I'll just stick with the pattern here and put a bracket on this one. All right, so -2 to 1. The last part we need to get is the quadratic. Okay, we can kind of eyeball this one as well. This point, this arrow's pointing to right here, okay, is actually going to be the vertex of our parabola. So our graph is first, our x value, looks like our vertex for a parabola typically be at the origin, so we're shifted to the right 1, which means we say x minus 1. Okay, we're going to be squaring it to make it quadratic. It's up here at 1, 2, so that means we had to move it up a vertical shift of 2 units. And then typically a parabola opens up. This one's opening downward, so meaning we had to have a negative in the front. And this occurs from 1 to infinity. So now we have our piecewise function for that particular graph. I'll talk about some other things like I said before when I get back. But there's a good start for analyzing piecewise functions. You guys have a great day.